We keep hearing that we need to do everything we can to avoid climate disaster. And one of the things we're told we need to do is get rid of fossil fuels. Easier said than done, right? After all, fossil fuels are what make modern life possible. They power our homes, our transportation systems, and a huge portion of our industrial processes. So while it's easy to favor renewable energy sources like solar and wind, they can't just turn off the lights when it gets dark or the wind stops blowing. We need something that's reliable and powerful to fill that gap. Nuclear energy could be part of the solution, but many countries are moving away from it because of the risk of nuclear accidents and the problem of nuclear waste. Wouldn't it be great if we could harness the power of the biggest, brightest star in our sky? You know, the one that gives us all of our light and warmth and makes photosynthesis possible and powers the water cycle and drives our weather and has been doing all of that reliably for billions of years. Yes, that sun. Could we bottle some of that solar power and bring it home? It might sound far-fetched, but scientists have put forward a few different plans to create a mini-sun here on Earth. But there are some big challenges that stand in the way. What is the sun fundamentally? A giant fusion reactor. The sun's enormous gravity holds tons of hydrogen atoms in its core. So close together, these hydrogen atoms smash into each other with enough force to overcome their natural repulsion and fuse into helium. This process releases energy, which escapes from the core as sunlight. For comparison, most nuclear power plants use nuclear fission to generate electricity. Instead of smashing atoms together, fission plants split atoms apart and then use the energy released to heat water and create steam, which spins turbines connected to generators. Nuclear fusion has long been seen as an almost holy grail of energy production. If we could create a mini-sun here on Earth, it could potentially solve our energy crisis forever. Fusion reactions produce far more energy than fission reactions, and the fuel is incredibly abundant. If you want to understand why the sun is such a good fit for our energy needs, we need to look at this graph called the power versus mass curve. On this graph, the x-axis shows the total power output of a power plant over its lifetime. The y-axis shows how much fuel is needed to make that power. You might recognize coal, uranium, and hydrogen on the list, but those aren't the only options. Some sources of energy may seem better than others on first glance, but as you learn more about them, they start looking worse. Take natural gas. For example, it looks pretty good in comparison to coal. However, when you consider that you need to extract it, process it, and transport it, the total picture changes. Even worse, once you burn the stuff, the net energy you end up with isn't actually that impressive. Compare that to nuclear fusion, where you need very little fuel to get a lot of energy. That square is actually pretty tiny in comparison to the other options. And if we could ever crack this energy source, it could potentially power our civilization indefinitely. But how does it compare to the power we get from the sun right now? We can see that the sun is actually somewhere between natural gas and coal in terms of energy return per unit of fuel. But remember, the sun is huge. To get the same amount of power from it that we do from burning fossil fuels, we'd need something like 4 million of these mini-suns to power our society. Still, it would be nice to be able to tap into the sun's seemingly endless supply of energy without waiting for it to recharge every 10 or so minutes. The sun is made mostly of hydrogen, but the type of hydrogen is not the same as the stuff that's used to fuel hydrogen cars. Cars can use liquid hydrogen, but it's extremely difficult to get hydrogen out of the sun. Instead, scientists are considering using two hydrogen isotopes called deuterium and tritium. Luckily for us, both are pretty easy to come by. Deuterium can be found in seawater, and tritium can be produced from lithium. Tritium is radioactive, but it doesn't have a large whole-body half-life. In other words, the half-life of radiation coming from tritium is relatively short. So after about 10 years, most of the tritium would decay into stable isotopes of elements around it on the periodic table. Also, any unused tritium could theoretically be recycled back into lithium. Now, you probably know that getting these atoms to fuse isn't going to be easy. Scientists have managed to achieve nuclear fusion under extreme conditions in labs, but the reaction ends up consuming more energy than it produces. That's because the reaction requires immense heat and pressure, even hotter than the sun's core. To put the temperature requirement into context, the sun's core reaches about 15 million degrees Celsius. For comparison, the hottest man-made plasma ever achieved on Earth was about 3.5 million degrees Celsius. That record was set in 2021 by the Joint European Torus, also known as JET, which is a tokamak reactor. Tokamaks are donut-shaped devices that contain and heat plasma. While JET's recent experiment was a success, it's still a far cry from what's needed to make a mini-sun. Another major hurdle is that these reactions don't just happen in an instant. Instead, the fuel needs to be kept at the right temperature and pressure for minutes at a time. That means anything that can't withstand those conditions won't be suitable for a fusion reactor. Scientists are working on finding the right combination of materials that can withstand the heat and pressure necessary for fusion. Finding those materials is hard enough at the temperatures and pressures we experience on Earth. But since no one has ever created a sustained fusion reaction hot enough to power a miniature sun, scientists have had to use indirect methods to find the right materials. Techniques like thermodynamic modeling and molecular dynamics simulations can predict how materials will hold up under extreme conditions. But this is all theoretical work. What scientists really need are experimental measurements. Fortunately, there's a project working on just that. In 2022, researchers from Princeton University in New Jersey began operating a device they built to test materials at the high temperatures and pressures found inside stars. Their device uses a powerful laser to heat a small sample of material to about 6,000 kelvins, which is about 5,700 degrees Celsius. At that temperature, the team can measure the strength of materials and observe how they degrade over time. While some of these experiments are underway, other groups are taking a different approach to creating a mini-sun. Instead of trying to build a reactor that can reach the required temperature and pressure, some scientists are attempting to find ways to reduce the temperature and pressure needed for fusion. For example, one group of researchers have proposed a device that uses lasers to squeeze hydrogen fuel into a dense plasma. Another team has proposed using shock waves to accomplish the same thing. Either way, if they can lower the requirements for fusion, we might not need to worry about whether or not we can create an environment as extreme as the sun's core. But even if we did manage to create that mini-sun, we still need to find a way to harness its power safely. Otherwise, it could pose a serious danger to the planet. There's also the issue of cost. Building any kind of fusion reactor is likely to be expensive. So even if we could build a mini-sun, it might not be worth the price tag. Ultimately, building a mini-sun may not be possible, but the research being done for this project may end up yielding other useful technologies. As always, there are multiple paths to achieving a clean energy future. While none of them are easy, we'll eventually need to transition off of fossil fuels. Until then, we'll keep searching for the perfect mini-sun. Maybe it'll end up powering our world someday. Or maybe we'll find a new energy source that's even better. Thanks for watching this episode. Like a sun, our channel depends on nuclear fusion to produce new episodes every week. You can help provide the heat and pressure needed to make that happen by hitting the like and subscribe button. Thanks for watching. Keep looking up.